So we're now going to discuss damped and forced oscillations. Because the mathematics in this part is quite complicated and probably more than you've covered in Maths 1A yet, you need second order differential equations, we're just going to cover this qualitatively. You will be presented with the equations, but you're not expected to be able to use or derive these. So the types of questions you'll be asked is you could be asked to discuss the relative sizes of forces, you could be asked to sketch graphs showing what's happening, or discuss the sign of the forces and things involved. So we'll start by looking at damped oscillations. Damped oscillations occur when there's forces, non-conservative forces, such as friction and air resistance involved, which take some of the energy away from the system. Okay, so imagine a spring. When we hang a mass from a spring and let it bounce up and down, the amplitude of the bounces slowly decreases as we've got air resistance acting on it. If we were to put the spring into a beaker of water or some other viscous fluid, the amplitude would decrease much more quickly because we've got this retarding force acting on it. The mass is actually giving some of its momentum to the particles in the fluid. The retarding force is proportional to the velocity, so F is equal to minus BV, where B is some constant for a given material. So the total force acting on this mass is now the force due to Hooke's law minus Kx minus BVx, and the total force from Newton's second law is just equal to MAx. Okay, so this is our formula here. Now we can write this as a differential equation. Minus kx stays the same, vx is dx dt, and ax is d squared x dt squared. So this is now a second order differential equation. So you don't need to be able to solve, but if you could solve it, the solution would be of this form. X is equal to ae to the minus b on 2mt cos omega t plus phi, where this omega is equal to k on m, which is our omega naught, the natural frequency of the spring, our old omega, minus b over 2m squared. So this is effectively a new amplitude, ae to the minus b on 2m. As t increases, this exponential term is going to get smaller and smaller, and so our amplitude is going to get smaller and smaller. And this cos omega t plus phi term will make it continue to oscillate. So let's have a look at a graph of this. Here's our envelope telling us how the amplitude of the motion is decreasing. It decreases as ae to the minus b on 2mt. And then within that envelope, it's oscillating as the cos omega t plus phi. Now omega isn't changing with time, but it is different to, it's no longer equal to k on m. It's got a b on 2m function in there as well. So how would the velocity and acceleration be affected with time? Well, in exactly the same way. Their amplitude would be decreasing with time, but you would continue to have these oscillations here. The velocity is going to be out of phase with the position in the same way it was for normal simple harmonic motion. So we've seen that damping can make the oscillations die out over time, but if the damping's very large, then it actually stops the oscillations altogether. So the value for B for which all the oscillations stopped is called critically damped. So looking at this omega term here, and remember we've got the cos omega t term, when this term here is equal to 0, then we've got cos of 0, which is 1, which means that we don't have any oscillations in that case. So this is critically damped when this b on 2m is equal to the square root of k on m, because that's what makes this 0. So that is the frequency which will stop all oscillations. If we end up with a b larger than that, then you can see that this becomes an imaginary number and we can't actually solve it mathematically anymore. But looking at this graph, this shows you what happens when b is quite small, we get the underdamped case, which was the case we were looking at before, where it continues to oscillate but the amplitude decreases. With a critically damped case, it drops off to 0 as we only have the a e to minus b on 2m t term. And if it's overdamped, it drops off a bit more slowly. You can't tell the difference just by looking between these two.